Hello everyone and welcome back to another video. In this video we want to talk about B+Tree Deletion Algorithm. And the reason we are looking back at this topic is that I've recently faced a bug in my B+Tree Deletion Algorithm. And I really wish that I have made this video sooner because I kinda have forgot how things work. So the first thing that we will do in this video is that we take a look at the algorithm. I have prepared the flowchart of how I have implemented the algorithm, and we will compare it to the code that I have written so far. But before we begin, I encourage you to first take a look at other videos on YouTube, as I think they provide a good explanation of the algorithm. What I am planning to do is to cover the algorithm in a flowchart and my own code. I will leave the link of these videos down in the description, but you can check channels like Q&A, Java T-Point, and also Simple Snippets. And all of them have covered B+Tree deletion algorithm. And I think you will get a very good knowledge checking all of these videos. Once we have covered the flowchart, I will explain how I have learned about the B+Tree deletion algorithm and the problems I faced during the implementation. And in the end, I will talk about the bug I have faced recently and a funny story on how I have tried fixing this bug, which took me a few days of work. So here is the flowchart. And I know it looks very big and complicated, but I hope as I explain how it works, things get more simple for you. And the thing is that when we take a look at the algorithm in the videos like the ones I have shown you, things are not as complicated as when you're implementing them. But at the same time, of course, flowcharts themselves sometimes make things more complicated than they need to be. So don't worry about it. We will cover everything, and I promise you things are easier than we see in the flowchart here. But the main reason I have created this flowchart was that I didn't want to go over all of the details in my code again whenever I face a new bug. Also, I understand that this is not the cleanest flowchart you have seen. It's a little bit messy. Maybe if one day I have more time, I will make it less complicated. Also, the code may look a little bit complicated as well. I don't think it really is, but the main reason that the code looks bloated, despite me using Java for this project, is that a lot of times we have to distinguish between the leaf node and the internal node, even though we want to get the same thing. For example, here I want to get the size of the key list in the node, but I have to get it in different ways depending on if the node is a leaf or it's not. And maybe that's the problem in my implementation of things, but you will see such if statements in a lot of places in this code. For example, when we are borrowing, we again check if the node is internal, or if it is not, we do something else. And the same thing happens in the merge. We check if it's an internal node or not. And there are also a lot of comments around here to explain why certain logic is implemented in a certain way. And if you're interested in very deep analysis of this code, I encourage you, as always, to check the repository. And the link to the repository is down in the caption. The class we are looking at is B+Tree index delete operation. So the first step, like before when we wanted to look for an index, is to traverse down the tree and find the leaf node that we think it may include the index. And in the code, you can see that we have a linked list called path. And using this static method, I can pass the path and the root and say which identifier or which index I'm looking for and what is the degree of the tree. And it will fill this path for me, which, as I've explained here, the path is list of nodes sorted from the leaf first and the root node last. So if we loop over this path and the I is 0, the first node in the path is a leaf node. So with the leaf node, we try to remove the key and the value and update the leaf node. I should also mention that this code is not complete yet. So for example, here I could see if the result is true, then I would update it. If the result is false, basically as I've shown here in the diagram. If we don't have the key in the leaf node, then the key is not found, and basically we have to end the process because our tree doesn't include the identifier or the key. So again, back to the diagram, we have loaded the path, we have grabbed the next item from the list, and for now we are checking the situation where we are working with the leaf node. So the node is leaf, we follow the yes, and we check if it contains the key. If it doesn't contain the key, it's the end of the process. But if it contains the key, we remove it and update the leaf node. And after that, we have to check if the node is underflown. And what that means is that the number of keys are less than minimum number of keys in the B+Tree. And minimum number of keys in the B+Tree is the ceiling of degree -1 divided by 2. Now, at the time of recording this video, I have realized there is a problem here. And if the leaf node is not underflown, we don't just end the process. We need to continue this loop here because maybe the key is still present in another internal node. So let me fix this. So if the leaf node is not underflown, we just continue the iteration. But let's not go this way for now because we will cover the internal nodes later. And let's say that the leaf node is underflown right now. So we follow this path. And this whole blue box here is the underflow logic, or where we have to fill the node. And you can see that this fill the node here is the method fill node. So whenever we want to fill a node, we check if we can borrow from the siblings. And the logic to borrow from the right or left sibling is that we check if the current node is the first child of its parent. If it is, it means that there is no sibling at the left and we only try to borrow from the right. Otherwise, we first try to borrow from the left, and if we couldn't, we try to borrow from right. And what this trying to borrow means, let's see here. We check if the key counts of the sibling is more than minimum keys of a node. And if that is true, we try to borrow from the node. So the logic of borrowing from next is explained here. We borrow a key from sibling at right, and we remove the sibling first child pointer and pass it to the child or the current node. You can check the details of the code yourself, but the logic of borrowing from other nodes is explained also in the videos that I have mentioned in the beginning of this video. So if we go back to the flowchart, if we can borrow from either of the siblings, we have to continue the recursion. So we need something like this. If we couldn't borrow from any of the siblings, then we have to merge this node with one of its siblings. And you can also see the same thing in the flowchart. We couldn't borrow from the right, we couldn't borrow from left, and we are here. And this whole orange section is about merging logic. So here's the code. The code itself looks a little bit complicated, so I continue with the flowchart here. When we want to merge a node with one of its siblings, we first have to grab a sibling from either left or right. In my code, the right node has priority here. And then we need to determine two variables, which is the node that we want to remove and which is the node that we want to merge to. By default, the node that we want to remove is the sibling, and the node that we want to merge to is the node that we are at. And remember, the node that we are at is the node that is underflown. So we would want to remove from the sibling and add it to the node that is underflown. However, if the sibling has more keys than the node that is underflown, we swap the node to remove and the node to merge. So if this happens, the node to remove becomes the underflown node and the node to merge to is the sibling node. Our next step is that for internal node, we grab all of the keys for the node that we want to remove and add them to the node that we want to merge to, which includes all of the child pointers as well. And we will add them at the beginning or the end, depending on the position of the keys. So for example, if the node to remove is after the node to merge, the pointers are appended, otherwise they're prepended. And for the leaf nodes, we move all of the key values from the node to remove and add them to the node we want to merge to. And of course, we have to keep it sorted. I understand that up here, we assume that the node is leaf, and we are talking about the underflow logic and the merge logic. But these two logics are not only for leaf nodes. That's why we see here how things work for internal nodes as well. So after that, the pointer to the node that we want to remove should also be removed from the parent. So we do that here. And we also hold the reference to the key that is removed in the parent, because we will use it here. So in the next step, we have to check if the parent is now empty, because maybe we only had one single key in the parent. And if parent is empty, we need to check if the node that we want to merge to is a leaf. If it is a leaf, then we add the key from here to the leaf node that we are merging to. And after this process, or if the node that we want to merge to is not a leaf, we check if the parent is root. If it is root, then we set the node that we are merging to as root, as a new root, and unset the parent as root. And despite the parent being root or not, we remove the parent. And if the parent keys are not empty, we just update the parent instead of removing it, because we have removed the key from the parent. And after that, we update the node that we want to merge to. And then we check if the node that you want to remove is a leaf. If it is a leaf, we connect the siblings. So the previous sibling leaf node of the node that we want to remove should be connected to the next node of the node that we want to remove. And after this, we just remove the node that we want to remove. And when this whole merge process is finished, we just go back to our recursion and grab the next item from the list, which for now we talked about the leaf node. So our next item will definitely be an internal node if any item exists. The first thing we do is that we check if the node that we are on is the last item in the list, which means it may be a root node or it once was. And we also check if it's empty or not. If both of these conditions are valid, then we don't do anything and just grab the next item, and there wouldn't be any next item because this is the last item. So the recursion ends. And you may wonder, why would this happen? If we go back to the merge logic, you can remember that we removed the key from the parent and the parent could become empty. And the parent could also be the root node, which in that case, we would unset it as the root and set the node that we wanted to merge to as a root. So when this happens, the previous root would become an empty node, which is no longer a root node. And that's why instead of checking for root, we checked for the last item here, because the node, after it is loaded into the RAM, is no longer a root node, and it is already removed from the disk as well. So if this condition is not true, we will check if the internal node contains the key. And if it doesn't contain the key, we simply go and check if it is underflown. And if it is underflown, then we simply follow the underflow logic, as we have discussed. And if it is not, we go back to our recursion. However, if the internal node contains the key, then we have two options. If the internal node is a root node, then we have to fill the root. And to do that, we will find the leaf node that stores the key and select the last key in the node and store it in the current node. And by key, I mean the key that we want to remove. And after this, we again go back and check if the root node is underflown. If the internal node contains the key, but it is not the root node, then we check if the key is the first key in the internal node. If it is, we check if the sibling at the left has more keys. And if it does, we get the predecessor and set it at the key in the index. And this index is the index of the key in the internal node. So we replace the keys here. And if it doesn't have more keys, or we have set the predecessor at this index, we continue to the iteration. And I should also fix here, because if you see the code here, we are checking if the number of the keys in the left node are more than the minimum number of keys, more or equal. So this section is here. If we didn't go for the left node, we check if the right node has more or equal keys than the minimum number of keys. If it does, we get the successor and set it at the key in the index. We talked about what is the index. And if we couldn't get any keys from the predecessor or successor, we again come back to merging logic. So we merge this node with one of its siblings. And we have covered the merge logic as well. And again, after the merge ends, we go back to the beginning and grab an item from the list. And as we do this, we remove the keys and balance the tree whenever we need it. Also, here is the logic of getting the predecessor or successor. The predecessor is the last key of the leaf if we follow the closest left path from a node, and the successor is the first key of the leaf if we follow the closest right path from a single node. So let me tell you how I learned about B+Tree Deletion Algorithm. The first thing that I did was that I looked at some websites that explained the algorithm, but despite them trying to cover all of the edge cases, I couldn't understand the algorithm itself. What I mean is that I didn't understand how I can implement it. I just understood some of the big picture. After that, I found a PDF of a very detailed article, which kinda looked like it was written by a professor. And it also had code examples in C language or maybe C++, but it was overcomplicated, and I don't think anybody enjoys reading codes in a PDF file. After that, I went over YouTube, which I found the most useful resources there, and understood more about the big picture. But I was still confused on how to code the algorithm. It was only then that I tried ChatGPT. And as you may guess, it wasn't the best experience. And I'm going to show you why. So for a while, I have talked about the B+Tree with the GPT, and I requested the GPT to implement the delete method for me. And it wrote some code, which if you take a look at the method names, it looks like what I'm having right now. So we have predecessor, successor, finding a key, filling a node, borrowing, and merging. It didn't cover all of the edge cases, and it also didn't follow my code structure. So for a while, I have tried to convince ChatGPT to follow my code structure, but I failed. However, eventually I decided to let that go and just read the algorithm from what it wrote. But then after a while, it started telling me that it is doing things that it wasn't doing in the code. For example, it talked about such thing, but I couldn't find it anywhere in the code, so it tried to add it. And after a while, we could go out of the bounds of the certain list. And then it completely forgot what I have asked it before. And when it tried to remember it, it began to create invalid statements or syntax. So it had its own ups and downs, but eventually it created a code for me that, despite not being totally valid, it gave me a very good idea on where to start. And what I did was that I copied this code, changed the syntax, made it the way that it makes sense in my project, and then I started finding bugs in it and fixing bugs for different cases and scenarios. And I also want to mention that I hope this won't ever be my approach to programming again, because I had to go through a lot of pain before I can make this work. After everything was finished, I compared the general logic in my code with the understanding I found from the videos and ChatGPT and all of the articles that I have read so far. And after testing the code that I wrote, it seemed like everything is working totally fine. At last, I want to talk about the bug that I have faced recently. The problem would happen when we want to try borrow from left or right. As you know, the type of the values in B+Tree nodes are different between internal and the leaf node. With the leaf node, the value types could be anything. In my implementation, sometimes the value of the B+Tree leaf nodes are pointers, and the other times they are probably unsigned longs. And the byte size of the value is determined here with the value index binary object factory size. However, when we are trying to borrow from left or right, we are not always dealing with leaf nodes. And that's why when the node is a leaf, we can get the key list like this. And otherwise, we should use this method because with internal tree nodes, we know that the type of the value is pointers. And this is what I meant when in the beginning of the video I said that a lot of the complexities in the code is because I have to do things differently between internal and leaf nodes. But fixing a bug, even as simple as this one, was very hard because it only happened when we tried to borrow from left or right. And I already had test cases where the value of the leaf nodes were of type pointers, so those one would still pass. But I have spent a few days tracing the problem, and it was sort of difficult to find the root cause. And to find the root cause and solve the issue, I had to go to my code step by step, visualize the tree that I have, and compare it to the tree that I should get. And it was then that I realized that at some point I'm losing some of the nodes in my tree. They're just getting empty, or the child pointers are lost. And eventually, when I took a deeper look at the code, I realized where the problem is.